Today I'm going to discuss what happens when good distributions go bad. More correctly, we're going to talk about one option for analyzing your data when the diagnostics tell you that your samples don't fit a known distribution such as the normal. And don't worry, if the diagnostics flag your data is non-normal, it's not the end of the world. And to illustrate this, I'm going to relate it back to my dissertation project, or at least a portion of my dissertation project. And to be fair, this is not actually how I'm analyzing my dissertation project, but it is applicable for this webinar. But before we start, let's go into a little bit of background. So when you talk about parametric data, what that means is the data come from a population that follows a known distribution. And typically in stats classes like this, when we talk about a known distribution, what we're talking about is the normal distribution. And that's characterized by, a bell-shaped curve, or a symmetrical bell-shaped curve where the mean, the median, and the mode are all the same. And if your data are normal, you have a world of options for analyzing it. You just have to choose which one's most appropriate. However, if your data don't fit a normal distribution, what's called non-parametric. All that means is they don't fit a known distribution. And the null hypothesis and alternative hypothesis are a little bit different for parametric and non-parametric tests, like the Kruskal-Wallis test. For Kruskal-Wallis, your null hypothesis is that your samples are from identical populations, and the alternative hypothesis is that your samples are not from identical populations. Pretty simple. So what are ANOVA assumptions? These are very important to know before you do start a test, and your diagnostics will tell you if your data fit or not. But for a parametric test, first of all, your data have to be normal. And they have to have equal variances among the groups or homoscedasticity, and you also have to have independence of errors. For non-parametric tests, the big thing that's different is that you drop the normality assumption. So all you have to have are equivalently shaped and scaled continuous distributions. However, that does include homoscedasticity. You have to have equal variances among your groups. A lot of people, even some of the literature that I've seen, seems to overlook that fact. At the bottom here you can see a data that come from a normal distribution that fit the bell-shaped curve, and data that are kind of bimodal and are non-parametric because they do not fit the bell-shaped curve. So that's kind of a visual of what we're talking about with parametric and non-parametric. So what are some pros and cons between the two ANOVA techniques? And when I refer to a non-parametric ANOVA, that's kind of a misnomer. The Kruskal-Wallis test, which we'll talk about here in a bit, it's not technically an ANOVA, but it's so similar to one that most people call it that. So I'm going to use that terminology throughout this webinar. So for a parametric ANOVA, one-way ANOVA, there are more assumptions that you have to meet. And conversely, with a non-parametric, obviously there's fewer assumptions. And the biggest difference is that with your parametric ANOVA, the normality assumption is very important, although it is fairly robust to deviations from normality. For non-parametric, there is no normality assumption, and frankly that's like throwing a life vest to a lot of graduate students. The parametric test is much more powerful than the non-parametric test. What I mean by power is the ability for the test to detect and flag a significant difference among the populations, among the samples, if one truly exists in the populations. So basically, if there is a difference, you're more likely to find it with a parametric test than the non-parametric Kruskal-Wallis test. Both of these tests are fairly robust to just little deviations here and there, as long as you meet the assumptions. You can't ignore the assumptions. So again, the big differences are, with a parametric test, you have much more power, more statistical power. And with the non-parametric Kruskal-Wallis test, frankly, it gives you flexibility to deviate from that normality assumption. So what do you do if your diagnostics flag that your data is not normal? Like I said, it's not the end of the world. You just have a few decisions to make. It seems like a lot of grad students just say, to hell with it, I'm going to quit and rejoin the workforce. Probably get a raise while you're doing it. But we're going to put that in the least preferred category. The first option you should look at is transforming your data using something like a log transformation or a power transformation, something along those lines. Basically, you want to manipulate your data to the point where it does meet the assumptions. And a lot of times that does work. However, if you try to transform your data and none of the transformations work, you can't pass the normality assumption, then you need to move on to a non-parametric test. And for this webinar, the non-parametric test that we're talking about is the Kruskal-Wallis test. At the bottom here, you're going to see the QQ plot, and this is one of the normality diagnostics that R will produce for you. And what you can see with mine here is that, and this is for bare ground, is that at higher values of bare ground, mine deviates from normality. It deviates from the line, which means it deviates from normality. So, moving into talking about my data as it relates to this webinar. First of all, I need to tell you a little bit about my project so you can understand how I'm using the data to discuss this topic. Basically what I want to do here is I want to talk about demographics and habitat characteristics of grazed native warm season grass pastures and tall fescue reference pastures. So, some things that we know about this system is it seems almost like native warm season grass pastures are the elusive potential win-win, meaning it's a win for wildlife and grassland birds and a win for agricultural producers. Anyone that's worked in private lands management knows that these sorts of win-wins just almost don't exist. When you do find one, you get really excited. But there are, so the things that we know about the system are that cattle gain really well on native warm season grasses in the summer, and if cattle that gain well are also highly profitable for producers. So win for producers, win for cattle. We also know that native warm season grasses provide excellent habitat for grassland birds in a conservation setting, like the Conservation Reserve Program or land managed by some sort of a wildlife agency or a conservation organization. However, what we don't know is if we plant native warm season grass pastures for agricultural production, for livestock production, if grassland birds will still benefit from them even though they're managed strictly for profit. So we need to find that out. We need to find out if grasses grazed in a pure for profit way will still benefit grassland birds. And once we know that, we can recommend them to producers who are looking to make money on their cattle and have grassland birds for wildlife viewing. So along those lines, what I want to do is to compare among my native warm season grass stocking rates and tall fescue reference pastures, avian demographics, specifically density of grassland birds, and habitat characteristics. And in this case, habitat characteristics are represented by vegetation measurements, because with wildlife, your vegetation is your habitat. So when I measure the vegetation, those numbers tell me about the suitability of the habitat for grassland birds. Similarly, density, if you get at avian density, you also know what abundance is. So that tells me how many birds are out there. I have a completely randomized design. It's well set up for an ANOVA. I have 3 treatments, 4 replicate pastures per treatment, and these pastures are representative of pastures in the fescue belt, which is my frame of inference. I'll be conducting this test over 3 years. Obviously for this presentation, only 2015 is represented. And my 3 treatments are basically, without going into them too deeply, I have 2 stocking rates for native warm season grasses, which is a continuous stocking rate, which is the traditional way of stocking, and what we call our heavy early stocking rate, which is a stocking rate that's made to more closely match the natural growth curve of native warm season grasses. And lastly, we have our tall fescue reference pastures that we're comparing both of these native warm season grass stocking rates to. That's because tall fescue is what's out there on the landscape, so it's the status quo. So we want to know how we're performing related to the status quo. So before we get started, this is just what my data structure looks like. As you can see, I have 3 treatments in that leftmost column, and I have 4 replicate pastures per treatment. Up there, DENS is density, measured in the number of birds per hectare, and then the other 2 variables that I'll be using for this presentation are bare ground, % bare ground, and % forb cover, and that's measured with a Daubenmeier frame. So when I ran my data, when I checked the diagnostics of my data before performing my ANOVAs, I had a few surprises. Basically, my data were not normal, or 3 of my variables did not pass the normality assumption. And to test this, I used a Shapiro-Wilk test. And basically, when you run the Shapiro-Wilk test, what you're looking at is a W value and a P value. You want your W value to be above 0.9 and your P value to be non-significant. Like with most diagnostics, you want your P values to be non-significant. And if you look at my values for these 3 variables, you can see that they are indeed below 0.9, some significantly, and they are highly significant P values. So that's bad. But again, it's not the end of the world. What do I do now? So my solution was to conduct a log transformation. And to do this, to test this, to make sure this worked, I ran a Shapiro-Wilks test using the log of the variable. And for me, this fixed normality problems with all 3 variables. And so I was able to go on and run ANOVAs and complete my analyses. However, that's not any fun, especially not for the purposes of this webinar. So what did I do? I just assumed that my transformations failed. When your transformations fail in an ANOVA framework, the thing that you move to is called a Kruskal-Wallis test. And again, it's very similar to a non-parametric one-way ANOVA, but it's not exactly the same. Again, big differences, it does not assume normality. What it does is it ranks your data. It ranks from greatest to least for all of the groups that you are testing for differences among. And then it examines these relationships among those groups to see if they come from the same population or the same distribution. So if you look at these, this is just a comparison of my results. For avian density, you can see that the p-value for the regular ANOVA, and this is of the log transformed variable, was 0.764. For the Kruskal-Wallis test, it actually went down a little bit to 0.7351. For bare ground, my log transformed ANOVA was 0.518. Not significant, obviously. For the Kruskal-Wallis test, also not significant, but it went down as well to 0.4425. For my FORB cover, I was pushing significance in my log transform data with 0.0644. On the Kruskal-Wallis test, the p-value did indeed go up, which is what I would expect, frankly, and it went up to 0.09212. Still not significant at the 0.05 level. And I was a little surprised by the avian density and the bare ground Kruskal-Wallis test. I expected that the p-value should be higher because it's less powerful, and I frankly can't tell you what happened there. The only thing that I can think of is that one thing I didn't tell you is that these 3 variables also failed the equal variance assumption. So by running the Kruskal-Wallis tests and violating the equal variance or the homoscedasticity assumption, perhaps by violating that assumption, I kind of fooled the Kruskal-Wallis test and give me a slightly lower p-value than was produced by the log transformed regular ANOVA, parametric ANOVA. So in conclusion, while it's easy to say, oh my God, yeah, this is great, no matter what happens, I can run a Kruskal-Wallis test on my data, even if it fails all the assumptions. You really don't want to do that. You're going to lose a lot of power, first of all, and second of all, it's not as robust of a test. There's a lot of things that you have to take into consideration, and it limits your interpretation of the test. So I'm going to stick with what Dr. Saxton says and just say, only use non-parametric tests, period, as a last resort only. So, like I said, it's like a lifeline. Use it if you need that lifeline, but avoid it if you can. Thank you. Have a good one.